All right, well, welcome everyone to this presentation. I'm Jason Richter. I'm the TL or technical liaison for this project, and it's titled Seismic Approach to Quality Management of HMA, like you see on the screen. Presenting today, we have Dr. Choon Park, as well as co-PIs or principal investigators, Drs. Nils Ryden and Josephine Starkhammer. And this will basically be a project update. This project got underway right around the turn of the year when we kicked off our first meeting with the TAP, which, goodness, seems like an eternity ago considering all that's happened since then. But anyway, this will probably be the first time this project's been presented to the full ICT team. So there are probably a few, if not many, who aren't too familiar with the goals of this project. So I'll just give a little bit of background before I turn it over to Choon. And sorry, Choon, if some of this becomes redundant in your presentation.
No problem.
Yeah, basically we're developing a device and software which will allow us to characterize newly paved HMA using shear wave velocity. And this device will initially measure surface wave velocity in a non-contact, multi-channel, rolling, in other words, constantly moving fashion. Rolling temperature measurements will also be taken at the same time. And these results will be processed and visualized in a 2D manner, giving surface maps as well as 3D volume models, which will be georeferenced so that they can be imported into the Veda software, which the AMT unit uses. As a bonus, the module that's in the software, it's also going to be capable of outputting layer thickness. So with all this talk of surface and shear waves, if it hasn't become apparent from that nomenclature, that this is a geophysics-based project, and thus it's going to require a highly advanced level of geophysical expertise, and this is where Dr. Park comes in. For those of us that work in the geotech engineering industry, he's basically a household name, and he's credited with the development of a seismic geophysical method, which we use in our section at MnDOT. It's termed the multi-channel analysis of surface waves, or MASW for short. It's a staple in our toolbox geophysics-wise. We've been using it for about 10 years now, and it works great as a subsurface characterization tool. So not surprisingly, a variation of this method, mainly on the high frequency end, is going to be employed on this project. And Choon also has extensive experience when it comes to coding software, so not surprisingly, he's going to be developing that on this. So the device and the software that are being developed here, they are a first, but it's not the first time something like this has been attempted. This actually expands on some work that was done by one of our co-PIs, Dr. Nils Ryden, who's on the call today, and he's been researching this approach for a few years now. You can look up one of his papers actually related to this effort. It's in the Journal of Road Materials and Pavement Design. I believe, Nils, you were awarded best paper for that in 2019, if I remember right. So we'll also hear from Dr. Josephine Starkhammer. She's an engineer behind the hardware development aspect of this device. She not only knows how to build stuff, but she brings a pretty extensive background in acoustics, which is essential to this project, considering that the seismic energy that we're measuring is in an acoustical state. So, by the way, both Nils and Josephine are calling in from Sweden today. So, I guess rounding it out, this group is, it's nothing short of a geophysical NDT and engineering all-star team. So with that said, I'll turn it over to Choon. He's our principal investigator. He'll give an update on the project. Choon is the founder and principal geophysicist of ParkSEIS-HMA, which is also run by his wife Jin, who's on the call today. If you want to learn more about their business, you can go to ParkSEIS-HMA.com. So there's your free sales pitch, Choon. But he's also created a link on the front page of his company website, and you could access information about the project, the updates, past presentations, including this one, meeting minutes and things like that. So what are the ground rules related to questions here, if I may ask? Do we just put them in the comments section or the IM section and then we address them later, or how are we doing that?
Are you asking to me or?
Lauren or Rebecca?
However you want to do it.
Okay. I mean, we can take them as they come in, or it's up to you, Choon.
What's your preference? So if you want to take them as they come in, we could have people put a question mark in the box, or if you want them just to type it in and wait for the end.
Yeah, I would rather wait until I'm done with the presentation.
Okay.
Probably after my presentation, Niels will have his own presentation immediately.
Okay.
So we would rather wait until both presentations will be done and then take questions.
All right. Sounds good. You can take it away, Choon.
Well, okay. Well, thanks a lot, Jay. I think your summary was so good and covered more than 90% of my presentation today.
All right. Let's call it good then.
Okay. So Jason covered a little bit about the background, the development of this project, and I will go through more details about the how this project developed from the beginning and who are involved and how we're gonna achieve the goal and what kind of results we will be delivering at the end of this project. So, yeah, again, this project was launched in this January, and still this is an ongoing project as a 2-year project. And this is trying to develop a system consisting of both the hardware and software components to inspect asphalt pavement layer by using a seismic technique. And I represent the ParkSEIS-HMA, which is the prime contractor for this project and oversighting the entire project during a 2-year contract period. And ParkSEIS-HMA is in charge of developing most of the software components. And this particular seismic technique that we are using for this project, which is called, as Jason mentioned previously, it is called the non-contact multi-channel seismic approach, but that was developed in Lund, Sweden by Dr. Ryden and Dr. Stockhammer. And that's why they are joining us and working for this project and providing all the technical consultations. And the Norfitech, well, they are joining this project through a business entity called the Norfitech. So Norfitech is in charge of developing all the 100% hardware components for this project. So there is a total of 4 investigators participating in this project, including Dr. Jim Park. She is joining this project as the operations and also administrative manager. So if you visit ParkSEIS-HMA homepage, you will find that there is a separate web page dedicated to this project. There you can find everything about this project. For example, there is a summary of the proposal and the representatives and detailed description of the scope of the work. And all the presentation files are there, technical advisory panel members, meetings, and monthly progresses are there. So if you wish to know more about this project, please feel free to visit there. So basically, we are trying to develop a system that evaluates stiffness and thickness of asphalt pavement layer by using a seismic technique. Stiffness is our main target prime parameter that we are trying to evaluate as much accurately as possible. And thickness is a kind of byproduct from our main approach to evaluate stiffness. And I believe most of you are involved in road business, so that we are familiar with the importance of evaluating these 2 parameters. So I'm not going to talk about why we are doing this. Instead, let me briefly talk about how we can do it. So first, stiffness. When it comes to stiffness of solid materials, that property commonly has been represented by so-called elastic moduli. There are 3 elastic moduli. One is called the Young's modulus, which is a measure of materials resistance along the longitudinal deformation. The other one is called shear modulus, which is a measure of materials resistance to transverse deformation. The last one is called the bulk modulus, which is materials resistance to volume change. So when it comes to geotechnical materials, these first 2 moduli are most appropriate. and also most important. So let's take a look at the defining equations for both moduli. Shear modulus has this defining equation, and Young's modulus has this defining equation. So we see there are three parameters. One is density, the other one is a Poisson's ratio, the last one is a shear wave velocity. And we see shear wave velocity is included as a square term in both defining equations. What that means is the shear wave velocity contributes most. In other words, if we are to measure only one parameter out of these three parameters, then it should be shear wave velocity because that contributes most. In addition, in reality, we know pretty good approximation values for the other two parameters of density and Poisson's ratio. For example, when we are dealing with asphalt pavement material, we know density is somewhere between 1.7 and 2.0 gram per cubic centimeters. And also Poisson's ratio is somewhere between 0.3 and 0.35. But shear wave velocity of certain asphalt material can be lower than 1,000 meters per second, and it can be higher than 2,000 meters per second for some other pavement material. In other words, it varies a lot. That's why we need to measure shear wave velocity as much accurately as possible to accurately define this shear modulus and Young's modulus. And that's why shear wave velocity has been used as a synonym to materials stiffness property. So in the late 1990s, there was a multi-channel seismic technique developed, which is called the MASW approach. And that has been dealing with the shear wave velocity estimation of common near-surface materials of soil and bedrock setting, and has been providing this kind of typical subsurface cross-section of shear wave velocity variation, where we see there is a bedrock here, and there is a soil layer in which we see shear wave velocities. So basically, stiffness properties change laterally and vertically. And then early 2000, Dr. Ryden first applied the MASW approach to this pavement for the evaluation of shear wave velocity or stiffness and thickness. But in comparison to normal MASW survey, which deals with the tens of meters depth and also horizontal distance of at least 100 meters or sometimes up to tens of kilometers, the dimension that he was dealing with at that time was a very, very small scale, almost a microscopic scale, because depth range was almost a few tens of centimeters. And also the horizontal distance that he was dealing with by using either shot array or a receive array was only a few meters. So he could not use that conventional geophones that was used for ordinary MASW surveys, because the geophones are good at recording only up to several hundred hertz of seismic waves. But here we have to deal with a few or several tens of kilohertz of seismic waves to resolve a very small scale with a very high resolution. So he had to use a very special device as a receiver, which is called the accelerometer, as shown here. And this is a very sensitive device, and you have to put coupling material. At that time, he used this grease to put on at the bottom of this accelerometer to ensure good coupling between accelerometer and the pavement surface. Otherwise, accelerometer cannot record the very high frequencies. And then he came up with this beautiful Lamb wave dispersion trend, where the type of surface wave that developed inside the pavement layer is called the Lamb waves. So basically, we are dealing with the Lamb waves. So he came up with this shear wave velocity of this pavement and the thickness in very accurate manner. So this approach at that time was considered as a phenomenal laboratory approach, but it was still far away from becoming a practical routine field approach, obviously because it took so much time. For example, to finish a measurement for one location, it took at least a half hour, and then there had to be 10 or 20 minutes of data analysis time. And the main drawback at that time was that this receiver, accelerometer, that required the good contact with the ground surface all the time. So if we calculate how long it's going to take by using this contact approach to inspect this one lane width of asphalt pavement of about 300 feet long distance, is with this 3 feet by 3 feet resolution, which is our current target resolution. Well, it's going to take 240 hours, which is 10 full days, which is completely unrealistic. He continued to improve it, and a few years later, Dr. Ryden completely eliminated the accelerometer, and he used the microphone hanging in the air by about 10 centimeters above the pavement surface, and came up with the identical result. And this one shows how it was possible to use a microphone to pick up seismic waves. Well, this is a snapshot of a numerical simulation of seismic wave propagation. This is a solid plate, which is basically a pavement layer, and this is a fluid, which is the air body here. So when we apply impact at the center of this setting, we see surface waves are generated and propagating along both directions. But at the same time, we see there is a small amount of surface wave energy leaked into air in the form of sound wave. This is called the leaky mode surface wave. That's why the microphone could pick up these leaky mode surface waves in the form of sound waves. So Dr. Ryden and his students came up with this apparatus, which is a 48-channel MEMS microphone array. In other words, there are 48 small microphones attached at the bottom of this array. One MEMS microphone is smaller than your thumbnail size. So 48 MEMS microphones are arranged at the bottom of this array with 0.75 centimeter spacing. So this total length is about 40 centimeters long. And this entire array was hanging in the air by about 10 centimeters above the pavement surface. And there is an impact source, solenoid impact source, electronically driven. So when you push a button, then it makes a small impact on the pavement surface. And then they came up with this beautiful result along a very short distance of transect, about 4 meters long. And we are looking at different colors representing shear wave velocities at different temperatures. We all know asphalt pavement stiffness changes with temperature. So I'm going to talk a little bit more about this temperature effect in a minute. So all of a sudden, everything can continuously move while the measurements are being made. But there was an issue at this time. There was the moving speed was too slow, probably slower than half mile per hour. The main obstacle was on this impact source. When everything was moving too fast, this impact source could not make a proper impact. He still continued to improve it, and then came up with this idea, which is a bouncing ball. This is a steel ball attached to this belt hanging down from this receiver array bar. This is a 48-channel MEMS microphone array. And so this steel ball, when everything is in motion, this steel ball will bounce up and down spontaneously, and it will make an impact. And I'm going to show you a very short video clip, but after my presentation, Dr. Ryden will show more detail the video showing how this works better. So, but let me show this one anyway. So this is the steel ball here, and you will see this steel ball moving up and down. And I could hear that impact sound very clearly, which means that impact was significant, generating a strong enough seismic waves. So at the end of this project, we will be delivering this kind of system consisting of multiple number of MEMS microphone arrays arranged along the transverse direction so that it can cover about the 1 lane width of asphalt pavement, which will be about 12 feet wide, or it can be half width, which will be 6 feet wide. But anyway, it will be covering certain width of asphalt pavement simultaneously while the survey vehicle is moving at a speed somewhere between 5 and 20 miles per hour. And then the onboard computer will be analyzing all the incoming seismic data in almost a pseudo real-time mode and display the output results in a 3D format similar to the one illustrated here. And I think that's Ryden will mention about this one again during his presentation. But we believe we may have a certain limit in terms of the continuous moving time, because we have to stop once in a while for system refreshment. Otherwise, too much seismic data cannot be continuously handled by the system. But we are trying to improve it so that we can continuously move as much long distance as possible at one time. So if we calculate how long this is going to take to cover the same area that I was considering, by using this non-contact approach, it's going to take only 218 seconds, which is less than 4 minutes. So if we compare this old fully contact approach, which will take 10 full days, this will take less than 4 minutes, which is a completely realistic approach. That's why we are developing this system. And this one shows a conceptual illustration of the final output results being displayed on the onboard computer screen. So for example, if the survey vehicle moves along this 1 lane width of the asphalt pavement, then on the computer screen, there will be this kind of this is a kind of a plan view map. This is about 1 lane width, which will continuously show the shear wave velocity variation along the pavement surface. And then there will be similar type of map being continuously constructed for temperature data. So for example, if we see any velocity anomaly on this map, we can actually refer to corresponding temperature map and see if these anomalies are related to temperature anomalies or not. So for that purposes, temperature display is very important. And then we can also display output results of shear wave velocities converted into a modulus, like a shear modulus and Young's modulus. And then we will show the thickness variation map as well. Currently, we are considering to use 2 different approaches for thickness evaluation. One is a Lamb wave based approach, which is our original approach proposed. And the other one we are considering is called the impact echo approach, which is completely independent approach. And I'm going to talk about why we are considering multiple approaches for thickness evaluation in a minute. So this is the hardware development stage. I believe Dr. Ryden and Dr. Stockhammer will talk a lot more about this hardware part on next presentation. But I want to make one point here. The original 48 channel receiver array, MEMS microphone array, is something that Dr. Ryden and Dr. Stockhammer developed for their own research purposes a few years ago in Lund, Sweden. And they have been using that system to collect pavement data from various different conditions, only for our optimization process for our receiver array. Because we don't know yet our one receiver array will have how many channels and what's the optimum distance between the channels. We don't know that those optimum configuration yet. But that's why Dr. Ryden and Dr. Stockhammer have been using their system to come up with that conclusion so far. So I think within next 1 or 2 months, we will make that decision and start building our own receiver array. This one is the software package for this project called the ParkSEIS-HMA. The parent software package is called the ParkSEIS, which was developed for normal MASW surveys dealing with a few tens of meters of soil and bedrock setting. But that software package has been under modification to meet needs for this project. And here we are looking at the beginning stage of user interfaces. Basically, there are 2 different modes. One is called the in-field mode, and the other one is called the in-office mode. In-field mode is the one that you use to go out in the field and collect the data. Once you hit that button, then there will be there will be all kinds of parameters that you need to set up in terms of recording and the field geometry. So once you are done, then you click this arm button. And at that time, you make all the system ready for collecting the seismic data. So once your survey vehicle starts moving, then it will automatically start collecting seismic data. And then the results will be being displayed on your computer screen in pseudo real-time mode. So that is the in-field mode. And in-office mode is something that at the end of your field survey outside, you would want to bring your laptop computer into your office. There you may want to do something else, like you may want to export all those results into different formats, or you may want to check all the intermediate results. Or sometimes you may want to run all the seismic data by through the entire process again by using advanced approach, which will take a lot longer time. But you can do it, you can let it run overnight, and then next morning you can check the results and compare how they compare to the results obtained in the field. So that's the in-office mode. Well, let me talk about one of the challenges for data analysis approach, which is how to properly handle direct airwaves. Whenever you make an impact on the pavement surface, you generate the seismic waves, which are propagating inside the pavement layer. But at the same time, you generate this sound wave, which is the bang sound whenever you make the impact. So that has a very significant energy in comparison to seismic waves inside the pavement layer. So if you display raw field data, you will see there is a very strong energy arrival pattern, which is nothing but direct air wave, which is nothing but our noise. There is the land waves barely seen here because these are so much dominating. So if you use this raw data as is to make this dispersion image, by the way, in surface wave methods, creating proper dispersion image is the most critical part of the analysis. Once you have very accurately defined dispersion image, then you have in very good shape to come up with very good results of your seismic shear wave velocity and thickness evaluation. So if you use this raw data as is and construct a dispersion image, all you will see is the phase velocities of these air waves, which is useless. That's why we need to get rid of this strong air waves through proper method. There are multiple ways to do that, and one of them is called the surgical mute, which turns out to be most effective to generate this well-developed land wave dispersion pattern. So only after we apply this surgical mute, we can see that our signal land wave wave field clearly. And at that time, we use that record to construct dispersion image, and then we will come up with this very well-developed dispersion trend of land wave. But still, there are some complications. As I said earlier, when we use the raw data as it is, the dispersion image will be useless. And when we apply our surgical mute with the most optimum window, then we can come up with this very well-developed dispersion pattern. But if we change our optimum surgical mute window slightly, then we may come up with the results noticeably different. So this is kind of challenging because everything has to be done automatically. There is no room for operators' manual involvement. So that's why it has been taken a lot of time to develop proper algorithms only to take care of this airwave arrival so far. And once we construct very good dispersion image like this, we go to high frequency portion, which is very important to evaluate shear wave velocity very accurately. And then we go to a little bit low frequency part where the dispersion trend becomes a little bit curved. This part is very critical for the accurate evaluation of the thickness. But sometimes, because of multiple reasons, this low frequency part is missing. And then our thickness evaluation may become unreliable. That's why we are considering another independent approach of impact echo as a supporting method for thickness evaluation. So this one shows our overall schedule. As I said earlier, this is a 2-year project, and the year 1 is aiming at the completion of 1D system, which is one of these MEMS microphone array and corresponding software package. And then year 2 will aim at the completion of the 2D system, which is the multiple MEMS microphone arrays arranged along the transverse direction. And we are somewhere over here, I believe we are somewhere between 30 and 40% done. And the next major task scheduled is the first joint field test, scheduled sometime in this fall to take place in Lund, Sweden. But I think we are considering now to have it like a remotely joint field test. For example, the team Sweden goes out to a specific site and collect the data and sends that data to us. And we go through our own software analysis. And then next day we have a conference meeting and go through a discussion for software and hardware tune-up purposes. And we can repeat that multiple times. And I think this is it for my presentation. And now Dr. Ryden will take over for his own presentation. Hello?
Hello. Thank you, Choon. Do you see my screen?
Yep, I can see it. Good.
Okay, so me and Josephine will show what we're doing right now and what we've been doing the last couple of months here in Sweden with the field testing and also development of the new data acquisition system. This is our local test site. It's called the Old Gunpowder Mill. It's kind of old famous mill in Sweden for gunpowder. And this is the way going to the mill. And it's kind of the best small road we have around here. So there's no traffic almost, so it's perfect. So we've been doing a lot of testing here with the old array, as Choon mentioned. And we're using this old array just to save time and money to come up with a best possible design for the 2D system. And lately we've been working on 2 subtasks within this task. The first one is the programming and configuration of the new data acquisition system. I call that DAQ or DAQ in these slides. And Josephine will talk more about that, and then I will show some examples from field testing here this summer. So Josephine will start with the software development for the data acquisition system.
Yes, thank you, Nils. As Nils and Choon mentioned, we have previously and in parallel to this project been working with an old system that is 12 years old now, and it's the old system is based on the NIPXI platform, which transfers data through the PCI bus, which is the same type of architecture as you all have in your own personal computers. But the new system, the one that you see here on this slide, is based on the much faster PCI Express bus. And it is in this context called NIPXE Express. And this is capable of faster data transfer rates from the analog to digital converters, which are circled basically there on the screen in yellow, to the motherboard and processor of the computer. So the transfer rate is faster in this new system compared to the old system. We also have added an infrared sensor for temperature measurements and the GPS for survey coordinates. Nils, you can switch slide. Thank you. So during our experiences so far in the field, we have discovered that we have the following challenges to deal with to make this project successful. We need, first of all, a very fast analog trig and retrigging capability in the system so that we can measure very closely spaced impacts. So the hardware system or the measurements part of the system must be really fast when we acquire the data. We also need a capability of asynchronous sampling of the temperature sensor and the GPS because the microphones will be sampled at a much higher rate compared to what the temperature and GPS can be sampled. So that's also one of the new things in the new system that we have been working with. Number 3, we have large amounts of data that needs to be handled in several parts of the program in parallel and at the same time streamed to the hard drive. And the 4th challenge is that we also need a very practical user interface for our initial field tests, like the ones that Nils will show you later on. We also need a hardware safe and data safe error handling capability in this new system, and also future compatibility with the ParkSEIS-HMA GUI in the future. And the solutions to these challenges, if we switch slide. Nils?
Don't you see the new slide?
No. Oh, yeah, now I do. Sorry. We have data acquisition software design, basically looking something like this. We have 6 parallel independent loops that each run in their own pace as fast as possible. And these are distributed over 4 cores on the computer or processor. For instance, we have one loop that deals with the user interface controls and reacts to event-driven actions. We have a measurement loop that is based on a state machine design with predefined states, which are all like looped through depending on what is happening in the measurements. We also have a separate display loop that displays data whenever data becomes available, and we have a GPS communication loop and temperature and GPS output loop, and a data logging loop that streams data to the hard drive as fast as it can whenever data becomes available. And in this program, the data logging loop will probably be the one that is our bottleneck, I would say, in how much impacts we will be able to acquire. So the state machine design combined with this kind of producer-consumer-based data acquisition method is meant to optimize the number of recordable impacts per foot, and this is directly related to the resolution of the final system. Also another thing that the parallel loops or independent loops helps out with is also the synchronous sampling. So the temperature and GPS is sampled for once every second. That's the maximum rate that most temperature and GPS sensors can be sampled, and outputs that to the measurement loop so that each measurement can be coupled with the most recent temperature and GPS position. And everything is clumped together and then in a separate loop logged to the hard drive. And in this slide, we see the current version of the user interface hardware controlling software, which I've been using in the lab so far with 4 channels, and me just tapping the floor with our source to just make sure everything is working in the lab. And once we have come up with the optimum configuration of the microphone array, we will start developing the microphone arrays or manufacturing the microphone arrays and connect them and start. Then after that, we will be able to start to do field testing for the first time with this new system.
Thank you, Josephine. I will continue with some pictures of the current field testing. As Josephine explained, the new equipment that we bought for this project has still been done inside and tested, and we're still working on that software. And to save time and money, we've been using the old array in the field testing just to optimize, because we don't have so many shots on building these MEMS microphone arrays. So we're using this old array, a 48 channel, which Choon showed before, which is a lot of channels. So we're using that just to come up with a final design, which may be 16 or 24 channels, or and also the optimum spacing between the MEMS microphones, and also the distance between the source and the array. So we have this kind of simple wood frame behind the car, and we have one source on each side of the array. The array or the microphones itself just look like an electronic circuit board, so there's no close-up in these photos, but you can see the main arrangement in this setup with 2 sources. And the reason why we're using 2 sources is because sometimes the array is not completely leveled with the pavement surface. And so if the array is not completely leveled with the pavement surface, we will get apparent velocity, which is a little bit biased because of the tilting of the array. But by using 2 sources from each direction, we can that error will be taken out if we average the results in the end. And it's also more efficient to have more than one source. So it's good to have one on each side. And we also want to have a robust source. It's, as Choon explained, we started with steel balls bouncing on the surface. And there's a lot of wear and tear on that steel ball. And it's a little bit difficult to attach. And we actually lost all our current steel balls. Nowhere to be found. And now we have more simple and cheap, just metal objects in plastic stripes, which works very good. And we also done this field testing to do measurements at warmer temperatures. Before we only had data on concrete and colder asphalt. But now this summer we came up to 96 degrees Fahrenheit, which is quite high for Sweden at least. And also we have quite stiff bitumen pavements here in Sweden, so or soft, I mean. So when we have these warm temperatures, they get really soft. So we wanted to have that data from the warmer conditions. And this is how it looks. This is the old GUI for the data acquisition with the old system when we drive along the car. And here we have some examples of data. So on the left we see on the top left we see the raw data just muted, but it's a 48 channel, so this is like the best we can get. And it's very small spacing, less than a centimeter, like 0.75 centimeters spacing. So we use this kind of optimum or full array just to see how we can reduce this data set and still come up with a good result. So to the right we see an example of just extracting 16 signals. And each signal is a mean value of 3 signals actually to the left. That is to enhance this surface wave and suppress the direct air wave Choon talked about before. So we have not come up with a final design, but hopefully we can do it with 16 channels. That means we can have 4 parallel arrays with our 64 channels. And on the bottom here you can see this dispersion curve Choon explained, and we can get the approximate shear wave velocity of 1,500 meters per second in this case. And another example at 35 degrees Celsius, 96 Fahrenheit. We're down at the shear wave velocity of only 1,100 meters per second. So our pavements get really soft in these temperatures. And we can still extract this shear wave velocity from the 16 channel record. And it's also, it should be noted that we have pretty good signal to noise all over the complete array, although it's a relatively high temperature. This is also a challenge with these measurements, that we get a lot of attenuation at high temperatures. So this means the source is powerful enough, and with this source we also get at least 1 impact per 3 feet, or a little bit better than that. And it also lasts so far. So I think we're quite close to a final design of the array within 1 or 2 months, as Choon said. And I also have a small video clip here just to show what it looks like when we're doing our testing. I know the video doesn't work so good on Skype, but I will try to show it. Maybe for some of us it works and for some not, depending on your connection. Here we have two different sources, and the one in front is doing more impacts per feet or meter. So that's a summary of the current testing we're doing right now in Sweden. And thank you very much.
Okay. Choon and Nils and Josephine, thanks for that update. Looks like we got a few minutes left. Haven't seen any questions come through, but I'll open it up now if there are any.
Hi, this
Sure,
is Ken Mazer.
Okay.
I was wondering if I could ask a question.
Go ahead, Ken.
I don't recall, Nils, you saying anything about the speed of data collection or the rate of travel. You might have, but I missed it. Could you comment
Yeah, I
on
think I didn't mention that, but right now we're driving in 30 kilometers an hour, which is 15 miles per hour, I guess.
that? Okay.
About that, but there's actually no theoretical limit in how fast we can go. It's mostly related to wind noise and the robustness of the source.
Okay.
So we've been collecting data at 50 kilometers an hour, also without any problem. But usually we do 30 kilometers an hour when we're testing.
And how frequently does your ball impact the pavement?
The small source, which was in the front, if you saw the video, the impact is distance is about 1 feet. That's kind of the smallest distance we can go down to right now when we're driving in this speed. So it's a little bit of balance of the weight of the source and the speed of the car, and also the roughness of the surface influences. So it looks like simple things, but yeah, there's many variables there.
Okay. Thank you. Very interesting.
Thank you.
I think I was there someone that was asking at the same time as Ken? Do they want to speak up?
Yeah, this is Kyle.
Okay.
I was curious if you could expand on the signal to noise ratio effect when you're measuring at the higher temperatures. You said it was still good. I'm just curious how much compared to when it was cooler out did it reduce, and if you think that might be a significant challenge moving forward.
Yes. Yeah, it also depends on the source. So now we're improving the sources all the time here, but we have data where the signal to noise is so bad that the surface wave is within the noise level when we have these warm conditions. So it's even when we have this good data, I would say the signal is only factor 10, 5 to 10 of the noise. We can still get good results, but it's not a huge signal to noise ratio. So it's definitely a bit challenging in warm temperatures, but the source is very important there.
Well, I guess to piggyback on that, and maybe Rebecca or someone in AMT who can speak to this, or even someone in pavements, is this something that would be used when we're, directly after paving? Because, if we're if signal to noise is an issue, well, is it even necessary that we measure when pavements are, newly paved?
I don't think so. So we could still grab it later. You know, at the start of the day, though, they'll want to do it when it's somewhat warmer, though, just to get an idea. They don't want to be, you know, so having something near real time is always helpful and stuff, but for final acceptance, it could be later. But I'm sure they're going to want to grab some. But they do use the nukes. I don't know, Kurt, do you have anything to expand on in here?
Well,
I mean, it's just a matter of what the tool can do and where we would be able to apply it. It could be something that you would wait till the project's done and then measure the whole project and say, okay, we got some areas we have questions about, we're going to core those areas, or, you know, so yes, that's a limitation we'd like to not have, but it's still pretty early to try and figure that out.
I would agree with that.
I have a comment there also. It's the shear wave velocity, which we're measuring, is very sensitive to temperature. So I think it will be quite hard to do the measurements when you don't have even temperature, like too early or right after the layering. But yeah, that is yet to be tested.
Is there any thoughts to try to normalize to the temperature if you were able to read surface temperature along with it? How difficult that would be?
Are you talking about the possible calibration of temperature into the measured, evaluated shear wave velocity?
Yeah, trying to get rid of the effect of the temperature on your.
Well, I think Niels can answer better, but my understanding so far is that is something that we can actually take advantage by using this system. In other words, once this system is available, because right now there is no theoretical relationship between temperature and a specific shear wave velocity, because that changes with the material. So we hope we will be able to, or someone who will be using this system will be able to establish that kind of empirical relationship. Niels, do you have any further comment?
Yes, we are recording temperature, but I think both results, temperature and shear wave velocity, will be very useful to further investigate these relations and to find maybe anomalies. You could plot shear wave velocity versus temperature if you have a new mix with homogeneous and constant material, for example. But otherwise, the temperature and the shear wave velocity relationship will be unique for each temperature, each mix, and that's kind of what we're after with these measurements.
So Kyle and Derek, I don't know if your question was answered or not. I know we were trying to differentiate between newly paved and just ambient temperature, but I don't know, Nils, where is that threshold, I guess, where the signal and the noise becomes a problem? What temperature would that be? I mean, is that a fair way to ask it?
Well, right now we can, the highest temperature we have is 96 degrees Fahrenheit, and we have good signal to noise ratio with the new sources. So I guess we could go even higher, but and that temperature may not sound much to you, but we also have a much stiffer bitumen, or softer, I mean, here in Sweden because of our climate. So the asphalt is really soft at that temperature.
Mm-hmm. Well, we can certainly reach the 90s on a summer day in Minnesota, at least our state, anyway. Going back to the beginning, there was a question about a plan to test on pavements with known distress, and I think at this point we're just looking at newly paved HMA, but I don't know, Nils, if you want to speak to what surface roughness, you know, how that could affect measurements.
Yeah, that affects the source and the bouncing of the source. a little bit, and also the frequency content we get. We want the highest possible frequencies, and we get that basically when a metal object is hitting a stone in the matrix. But if we just hit bitumen, we will get lower frequency content and overall lower amplitude. And that's kind of inherent with all these kind of seismic tests on pavements. So we cannot control that. So I guess our approach is to do a lot of measurements so that we will get a lot of good measurements.
Mm-hmm.
But I think if we hit the bitumen when it's soft, we will not have good data.
Mm.
So it will depend on the roughness and the texture, like surface texture, how many stones you can see and how much bitumen is on the surface, probably. But we don't know much about that. But we can see it in the testing we've done so far.
Mm. So I'm assuming the question is referring to mainly, characterizing maybe in a scoping phase as opposed to just following paving. And I guess at this point we're mainly focusing on new pavement. So, so Mike, hopefully that answers your question. Okay. Well, we've reached the end of the hour. I guess I'm fine with going on. Otherwise, seeing no more questions, we can adjourn here. Unless I'll give somebody an opportunity to throw one in there if they still have one.
This is Kurt in North Dakota.
Sure.
I was just kind of maybe I missed it, but how do you like on a new pavement now? If you have two lifts, how do you differentiate between the two lifts?
Yeah, that's a good question. Right now we don't differentiate. We just get an average shear wave velocity of the thickness that we are sensing. There's theoretical possibilities to differentiate, but it will probably take too much processing at this stage. So we will get one average number of the complete thickness.
Okay.
Okay, thanks.
See a message being typed. Kyle, you can go ahead and speak too if you want.
Yeah. How would a temperature gradient affect the results, whether it's a new lift on top of a old one, or if it's warmer near the surface just because of the sun drenching of the pavement? Do you have any idea on how that might affect the shear wave velocity?
Yeah, I think that can affect quite a lot. So probably the best conditions to do measurements is like mornings or before the sun has been burning or creating a too strong gradient. But that is also yet to be tested. But the frequencies we're measuring are sensing different thicknesses in the asphalt layer, and so when we're just lumping it all together to an average shear wave velocity, then it will be an average also of the influenced by the temperature gradient, since the shear wave velocity will change with temperature. So if we have strong gradient, it can affect quite a lot.
Any more?
I had a question regarding the GPS accuracy. What kind of accuracy do you need to achieve, and is this going to be something that can be swapped out with different GPS units, or is it going to be integrated?
Josephine?
The GPS accuracy right now, I think it was, I don't remember actually, but I think it was somewhere around 1 meter or 2 meters. Niels, do you remember?
Yeah, I think it says 1 meter. It's just the ordinary GPS for navigation softwares.
But if this needs to be upgraded, I'm sure that there are options with more like a, with other systems, with one stationary GPS and one on the system that can communicate to each other. I think there are other systems that are more accurate than this. So, and I'm sure it could be implemented in the future if we see a need for it.
Well, Rebecca, most of these paving projects have a base station somewhere they tap into, right?
Correct. Yeah, we either use a local ground base station like what you're saying, or we have a CORS network, a virtual system across the state that we can tap into if we have good cell coverage.
So the system will be programmed so that the GPS communication part of the program can be easily switched to another system if that is needed. So.
Yeah, and there's other states that are set up the same to answer that.
And those accuracies are usually to the inch or within 4 inches, right?
For that, so it just depends on what a given state, because we want to be more general versus just Minnesota, but it just depends on what state each state will require for accuracy. But yeah, if you're connected to the RTK, we can get it within the 2 inches accuracy and stuff. So you should be able to swap it out to do that. And Schneider's on here; he can elaborate if people really want to get in detail of that and stuff. So, but some states might not need the high accuracy, and other states might desire that for the data. It just depends on how it's being used.
Did that answer the question?
Yep. Thank you.
Okay. Cellular corrections rather than base stations. I can't speak to that unless somebody else can. Anybody else see Paul's comment?
This is Jim Schneider. I can speak to it a little bit.
Okay.
It just depends on the size of the project and the distance. For a ground-based station, you can go, upward, depending on your radio and the power you have supplied to the radio and that you're broadcasting at. You can go, miles at a time from a base station and still receive your correction. With the CORS network, it still creates you a virtual base. So, you're still limited to an extent where you don't want to collect, more than a few miles at a time and then kind of stop and let it reorient itself, and then you can collect again. But as long as they're open to having the flexibility to have other receivers connect to the software, I think it'll suit everybody's need. I'm assuming the one that they have hooked up to it right now is just sending out that NMEA GGA sentence, which is, the system itself doesn't know the difference if it's high accuracy or not. It just it's a sentence that come out. It's whether or not the coordinates are correct or not, and it should still accept it even if you are connected to an RTK or getting, sub-meter accuracy coordinates. So sounds like everything's in line to possibly meet or be configured to meet everybody's needs, so we should be all right.
All right. Thanks, Jim. Okay. And with that, I think I'm going to adjourn this. If you guys have any more specific questions, you can go to the ICT team webpage for the specific project. You can ask our presenters' emails are on there, so if you got any questions, you go through that route. Choon, Nils, and Josephine, thanks for joining today. Josephine, thanks for hanging on a little while longer. I know you had to leave, but appreciate you sticking around. So with that, I guess we'll call quits here, and thanks for joining again, and